Hi, my name is Grant Ho, and today I'll be presenting joint work with Dan Boneh and Ballard and Niels Provos of Google Safe Browsing. Our work investigates are browser red pills possible to construct. And so some terminology, what are red pills? Well, red pills are pieces of code that can distinguish between a real execution environment and an emulated or virtualized environment. And I'm going to make a further distinction between native red pills, which are red pills that execute directly on the operating system. So you can think of these as red pills embedded in applications or executables that run directly on the OS. And browser red pills, which will be the focus of this talk, are red pills embedded in web pages, and they execute within the context of the browser sandbox. So a lot of prior work has actually been done on native red pills. So at Black Hat 2005, Joanna Rudawaska introduced the original native red pill. And since then, there have been many other papers written on native red pill techniques. And I should note that at Thursday, at the main conference, there will actually be a paper by Shi and collaborators at USC on native red pill techniques. But the key problem with trying to use native red pill techniques for browser red pills is that native red pill techniques rely on low-level operations. So they examine registers, they look for debugging processes that might be used in the VM, and other such low-level configuration detections. But when you think about browser red pills, right, these are JavaScript-based red pills that run within the browser. JavaScript can't examine contents of specific registers, they can't look at the processes running on the machine, and they can't use a lot of the low-level techniques that red pills use. So this talk will focus on how we design browser red pills in spite of these computational limitations. So why do we even want browser red pills? Well, if we consider an attacker who has a malicious website, if for concreteness assume that this malicious website serves a zero-day drive-by download. Well, these are very expensive nowadays, but there are a lot of anti-malware systems that actively seek out malicious content on the web. So consider Google Safe Browsing or Microsoft Smart Screen. These are large-scale anti-malware systems that use honeypots, which are instrumented VMs, to crawl the web and look for malicious websites. And if they detect that your website serves malicious traffic, they'll issue warnings against users that stop them from visiting your website. So as an attacker, your goal is very clear, right? You want to deliver your malicious web content to normal users, but you want to act benignly when you detect a honeypot or a VM is visiting your website. And so we imagine our red pills envisioning or sort of making this goal possible in the following way. So we have our malicious website, and a visitor views this web page. The attacker does not know whether the visitor is a real user or a VM, but we serve them our malicious landing page. Now, this landing page will execute our browser red pills in the visitor's browser, and these results will be sent back to our malicious website. Now, if the attacker detects from the red pill results that a real user is visiting our website, we can serve them malicious content. But if the red pills indicate that the VM is visiting the website, we act benignly or redirect them to a benign website. And so how do we construct these browser red pills? Well, as I mentioned earlier, we can't rely on the native red pill techniques of detecting low-level anomalies. But what about performance anomalies? Because honeypots are virtualized or emulated browsers or VMs, you can imagine that virtualization leads to altered behavior or performance of certain operations. And so the main idea behind our red pills is that we're going to execute certain JavaScript operations, which we believe to have a performance difference between VMs and real machines. And we're going to call these JavaScript operations differential operations because the hope is that they can differentiate between a real machine and a VM. There's an additional problem, though, in that because we're using performance differences, how do we account for users who have anomalous performance as a result of background activity or different hardware? Right? The raw execution times of operations are going to be unreliable if background load can distort them. And so the idea and solution that we use is that we're going to use relative timing measurements. And specifically, what we're going to do is first we're going to run a simple JavaScript operation. And we're going to call this our baseline operation. And the goal of this operation is to sort of gauge the background load or base performance of the visiting machine. And this baseline operation should have the property that it performs about the same on a real machine and a VM. What's going to alter its performance is whether or not there's contested resources, in other words, background activity on the machine. And so now our final red pill time measurement is actually going to be a ratio. We're going to divide our differential operation by this baseline time and return the resulting fraction. And I should note that I'm talking about measuring execution time. Because these are JavaScript red pills, we measure our timing in JavaScript, and this has a granularity of 1 millisecond. So now the complete browser red pill has 3 steps. And remember, this returns a number, which is a timing ratio. We first execute our baseline operation and measure its execution time. And afterwards, we execute our differential operation and measure its execution time. And we return the final ratio. And intuitively, you can think of it as follows, right? We execute our baseline operation and put it in the denominator to cancel out the effect of background noise. This, in a sense, gives our differential operation a clean environment to run in. And hopefully, the performance difference will sort of be indicative of whether or not this is really a VM or a real machine. And so for concreteness, our paper discusses the specifics of our differential and baseline operations in more detail. But we sort of have 3 categories of differential operations, so we try 6. There was writing to console, reading and writing from local storage. We tried thread work, so we spawned web workers, which are JavaScript threads. We measured context switching with JavaScript threads. We also measured the communication latency between the CPU and GPU, and just tested the capacity of the graphics card by rendering complex graphics. And for all 6 of these differential operations, we paired them with one of 2 baseline operations to create our red pills. So the first baseline operation is repeatedly appending lots of text to a DOM node, and the second baseline operation is allocating large chunks of memory. And you can imagine that these 2 baseline operations are slower with background load running on the machine, but in our empirical evaluation, they ran about the same speed between a VM and a real machine. And so this gives us a total of 12 red pills, right? We pair each of our differential operations with both of these baseline operations. So how do we determine what makes a good red pill? Well, first, our testing environment. We ran the 2-lace versions of Windows on a real machine, a VM with binary translation, and a VM with hardware-assisted virtualization. So this is 6 system environments. And on each of these system environments, we ran the 3 most popular browsers, and these were the latest versions at the time of testing. And so this gives us a total of 18 testing environments. We pick a browser to run in a certain machine in a given operating system. Now, for each of these testing environments, we loaded our red pill web page 100 times. Right? And so what this gives us now is a timing distribution for our red pills on a real machine, a VM with binary translation, and a VM with hardware-assisted virtualization. So now what do we want to do? Well, for each red pill, we look at all combinations of browsers and operating systems, and we compare our timing distributions of the real machine against the VM with binary translation. We then make the same comparison for our real machine against the VM with hardware-assisted virtualization. And when comparing these 2 distributions, we want to answer the key question, is there a significant and practical difference between these timing distributions on a VM and a real machine? Because this will tell us if the red pill is effective at distinguishing a real machine from a VM. So how do we determine this? Well, we had 2 criteria, and we required that both be satisfied. The first is that we ran a t-test comparing the VM timing ratios against the non-VM timing ratios. And we asked, does this t-test produce a p-value of less than 0.05? And this indicates statistical significance in a difference between the 2 distributions. And I'll explain this in more detail in future slides. The second criteria is that we want this to be a practical and easy cutoff to give an attacker in order to be able to distinguish between the VM and a real machine. So we said, is there a small overlap between the timing distributions of a VM and a real machine? And so now in detail, the first criteria is an independent 2-sample t-test. And it was a Welch's t-test specifically. So the assumptions of this t-test are that we give it 2 independent samples, but we don't know the underlying population variance, which is exactly what we have. We don't know the underlying timing variance of our red pills across every machine in the world. But we do have these 2 independent samples, namely the timing samples from our real machine and the timing samples from our VM. And so canonically, what the diagram looks like is we have these distributions A and B, and you can think of this as our real machine timing ratios and our VM timing ratios. And when we give the Welch's t-test 2 samples from these distributions, it answers the question, are these distributions statistically and significantly different? And so I mentioned that we use something called a p-value. Well, a p-value from a t-test is the probability that there's no statistical difference between the 2 distributions. In other words, we want the p-value to be very low because we want there to be a significant difference. And so I think somewhat of a standard in statistics is to use a p-value of less than 0.05. But I'll note that all of our successful red pills have a p-value of less than 10 to the negative 6. So this means with probability 1 minus 10 to the negative 6, which is basically 100%, there is a statistically significant difference between the red pill timing measurements of our VM and non-VM for successful red pills. The second criteria is sort of more of a fuzzy criteria. And we sort of used a magic number cutoff here. We basically wanted to give an attacker a very easy criteria by which to determine if a visitor's timing measurement is indicative of a VM or not. So what we simply said is that take 1 standard deviation away from the VM's average timing ratio, and then take 1 standard deviation away from the real machine's average timing ratio, and these distributions should not overlap. And in essence, what this allows an attacker to do is say, I have a visitor's timing measurement now. Is this visitor's timing measurement within 1 standard deviation of the real machine's average timing ratio? If it is, then we can sort of conclude that the visitor is a real machine and serve our malicious content. And so based on this criteria, what were successful red pills? And our paper goes into specifics of which red pills work specifically for what environments and has a lot more analysis. But at a high-level overview, if you look at the chart shows the number of successful red pills per environment that could distinguish between a VM and a non-VM. And the key takeaway here is that we have multiple red pills for every single environment we tested on. So regardless of the major browser you used, regardless of the 2 latest versions of Windows you use, and regardless of whether or not your VM uses hardware-assisted virtualization or not, we can distinguish between a real machine and the VM. And I should note, we also ran a follow-up experiment, which is discussed in our paper, where we test the effects of background load and sort of test the efficacy of our baseline operation. And we found that most of our red pills worked, in fact, all but 1. And so that still left us full coverage for every testing environment. And so now the efficacy of our red pills sort of leads to questions about how we defend against them. And so briefly before I conclude, as a honeypot, you might think that you want to trick a red pill into believing you're a real machine. So the first defense you might try is to distort time in the honeypot. Since the honeypot is an instrument VM that anti-malware organizations set up, we own the browser, we own the operating system, we can replace the JavaScript timing API with fake functions of our own. And these fake timing functions will simply alter the time returned to make our VM look like it's executing faster. The next technique you might try is to replace expensive JavaScript operations with fake operations. So consider graphics rendering. Rather than actually rendering the full graphic, you might just return early, which will again make your VM look faster and possibly like a real machine. Unfortunately, we think these are somewhat weak defenses. So if you consider, I don't know, replacing graphics operations with a fake function, one thing an attacker can do is, since he knows his red pill, he can just run the red pill web page on his own machine, and he can look at the final canvas. And he can choose a random coordinate on this canvas and store its RGB value on the servers. Then, for the red pill web page, in addition to returning the timing ratios, he can simply pull this coordinate off the visitor's canvas and send it along with red pills. And at the server end, the attacker can just compare the visitor's RGB value with his expected value. And if they don't match, then that's indicative of potentially a cheating honeypot. So if we can't trick red pills into believing that a honeypot is a real machine, why don't we just try and detect evasive JavaScript, right? The idea is that benign web pages don't really have a whole lot of reason to use red pills. And so our red pills had two operations. They had the differential operations, which it's sort of unclear how you would detect these, right? Our differential operations are fairly common, writing to console, rendering graphics. So it's unclear whether these are indicative of maliciousness. But what you might have a better hope of doing as a honeypot is detecting our baseline operations. Remember, our two baseline operations are repeatedly writing lots of text to a DOM node and allocating large chunks of memory. And these might look somewhat suspicious. And so this is more of a hopeful, more practical defense, possibly. And there's also been recent work done actually at last year's USENIX conference, and I should say at this Thursday session again, there will be work by Karat and collaborators at UCSB that do something similar to this. And the idea here is that you can render your web page in a non-VM and a VM, and you can compare the rendered content and the system state against each other. And if there is a significant difference between the rendered content or system state, that's likely indicative of some sort of evasive behavior or different behavior by JavaScript in a VM and non-VM. And so to conclude, first, browser red pills are possible. Even though we can't use native red pill techniques, we can use timing and performance analysis to overcome the limits of the browser sandbox in JavaScript language. And we can use baseline operations to resolve background load and get reliable performing analysis. These browser red pills are highly effective, right? They worked, again, against the three major browsers on the two latest versions of Windows. And even if your VM uses hardware-assisted virtualization or binary translation, the red pills worked. And so in terms of defenses, detecting baseline operations is probably the most promising defense. And we have a number of future work items that we mentioned in our paper in more detail. But since I'm out of time, are there any questions?
I'm just curious as to what the user experience is like during the timing analysis. So how long does this
Right. So most of our red pills execute under a second. With the complex graphics rendering, since we do a lot of heavy computation, this can actually take a few seconds. So I think our most complex graphics operation took about 8 seconds. So that might not be entirely practical at the time, but for instance, reading and writing from local storage is maybe 500 milliseconds total for the timing operation.
Thanks.
Luke Bezatels from North Carolina State University. I have a clarification question.
Sure.
It wasn't really in your slideshow, but you went over it briefly. You said something like a canvas attack looking for RGB values of a pixel. Can you discuss that again?
Oh, right. So the idea is, for a defense, if you tried to cheat on complex operations, for instance, if you tried to return early from graphics operations, right, what an attacker can do to detect a VM that's doing this is sort of have his graphics red pill, load it on his own machine, pick a random coordinate on the canvas, right, and this is now the final coordinate, that the RGB value that should appear if the red pill is executed. And then for each visitor, in addition to recording the time measurements of that graphics operation, he can choose the coordinate from the canvas on the visitor machine and return the RGB value as well. If they don't match, that's likely indicative that the operation wasn't faithfully executed.
Okay, I understand. So it's just for graphics rendering.
Yeah.
All right. Thank you.
Okay, sure.
Hi, Carl Kosher, University of Washington. So if you can't really hide the fact that you're running in a VM, do you think it is feasible to modify browsers such that the JavaScript always thinks that it's running in a VM?
Oh, so this is sort of a broad defense that you deploy widely. It's unclear how you do that, right? Unless you want to sort of compromise normal JavaScript. I mean, I guess there's a particular defense in mind, or?
No, the thought was just crossing my head that some version of Windows have really poor timing resolution.
Right.
So perhaps instead of hiding the fact that you're in a VM, just make the timing resolution poor enough that you can't really tell.
So that might work. The only concern there is that, for instance, JavaScript games or sort of web games, they might want, the precision of 1 millisecond. Right.
Marat, University of Tokyo. Did you compare your results to the canvas fingerprinting technique?
So there are, so for context, the canvas fingerprint technique is sort of a technique used. This is Hobob's work, I guess you're referring to?
No, when you render 3D text or like text and then see how it's actually rendered based on GPU.
So that technique and that attack is to fingerprint user machines, and so the idea is sort of it's a cookieless fingerprint. And so that's not exactly the same as our work because, there's nothing different necessarily about a real machine and a VM in terms of what it renders, right? Like how would you fingerprint the VM a priori?
But GPU is different, right? I mean, it's virtual GPU versus like real GPU.
Right, and so I guess that's what our graphics red pill is meant to detect. But you would sort of need to know specifically, I guess, what the virtual GPU would be that you're trying to fingerprint, I guess?
Yeah, and a little second question. So since you're from Stanford, did you try to run your crypto library that runs like multiple MD5 like say operations or like?
So sort of just running cryptographic operations in the browser. So this is Dan's work, and I am Dan's student, or I guess it was. We didn't try that. We were sort of going for more simple and quick operations, but that might be an idea. Yeah.
Thanks.
So to be valuable, you
Right.
kind of have to know the baseline and then know what it is that you're trying to measure and then compare the difference, right? So if you're, like you have to know, so if an attacker comes onto a machine, he doesn't know what the baseline is for a non-virtualized environment, right? So if you're going to try to determine whether you're in a virtualized environment, you have to have that baseline for that configuration, for that CPU, for that power, for that GPU, right?
Potentially,
so how
I
do you
guess
get that information?
the baseline operation, the idea was that you could scale your differential operation based on whatever hardware or background load you had on your machine. So you'll execute this on the visitor machine anyways. And you never look at the raw baseline operation, right? It's just meant to scale your differential operation, right? Which will probably have similar performance differences that result
But you
from
don't know
hardware.
what the differences should be, right? So you could technically go into a machine and it might be a slower machine with an older CPU that you now run and say, oh, this is a slower machine.
No.
It looks like it's in a VM because it's slower.
But the idea is that we return a ratio, right? So we execute our differential operation and our baseline operation on the visitor machine. And so both will have this lag or slowdown that results from the machine. And since we take the ratio, the idea is that sort of this extra noise from different hardware and background activity sort of cancels each other out.
Okay.
in the
And have
ratio.
you thought about trying to target more of a lightweight hypervisor instead of VMware?
So we use VMware with hardware-assisted virtualization. So that ran pretty fast relative.
So like I know like FireEye has a custom, hypervisor that's super thin, right? And they
Right.
might not do I/O. They might not.
So we couldn't really test on those sort of more industrial, I guess, VMs. We do have safe browsing VMs,
Right.
but since I'm interning on safe browsing right now, I don't want to talk too much about their VMs.
Yeah, I understand. What I'm saying is it might be more valuable to understand if this is actually a concern for those types of VMs.
Right. I guess the idea is that yeah, that's a valid point. In terms of testing, we didn't have a good way to test that, though.
Okay.
Yeah. Any more? Okay. Thank you.